distance, C to D 1.25 horizontal distance. You're right. But what would be the difference?
Because
I'll show you what's the difference. What I'm doing now is a centroid. You make a statement that CD has the same distance as DE. Okay. What is the difference is this is now your what? Your Y bar. Whereas the other one, this is your what? Y bar. That is the difference.
I see.
Okay.
Yeah.
Now you see I'm better. Not just okay. I'm not okay with you when you say okay. Okay. Any other questions on this? Okay, no. Now there is one question. Okay, there is one question. So this is okay, before I think that this is a very difficult question. Any question you all need to ask about thin wall analysis from the homework? Anyone, please? Or from your notes? Anyone? I hope this is a very clear example because as I said, the formula is very easy. The first moment of area is sometimes quite confusing to calculate. Excuse me. Okay. Any other questions for thin wall? The thin wall, as I said, is difficult. Okay. Now the next one, I'm going to ask you if you have question, any particular question. So let's go into the next section, which is I think is easier, which is known as the shear stress. For non-thin wall analysis. Anyone? Any question? Or if you are okay, then we will go into bending.
Could you
Felicity.
do an example of plotting like the shear stress distribution?
Okay, shear stress. So if I were to, do you mind if I do question number 5?
Sure.
Okay, I'll do question number. Yeah, question number 5 has a question number 5 is quite tricky. Okay, when I did not know it was so tricky until I looked at this. So homework. So example, I think couldn't remember now. Example number 1 now. So this is 1. Okay, whatever. I just got example. I do apologize. So example. So I will not calculate the first moment of area, all these, okay? Those are there already. So we know that so this is non-thin wall. And then we have homework 5, question 5. Okay, so let me get that image. Okay. So this is the image, and I'm going to call this my X, Y, and Z. And we are going to have I, Z, Z. I'm not going to calculate all these, okay? I'm just going to, is 872.49. And then the Y bar is 5.0153. So if I'm going to sketch, so we are given the distance from here to here, right? 5.0 5.1053. Okay. So we are going to plot. Okay, we are going to form the equation of the shear stress distribution. Okay. So the general formula that we are going to use, okay, is equal to Q, okay, as a function of Y is equal to width bracket C minus Y close bracket C plus Y multiplied by half. Okay, so C is the maximum distance from centroid. Okay, that is our C. Okay. So as I said, the first moment of area is the most difficult. So we are going to consider above the centroid, where now the thickness, okay, so the thickness is 368. So the thickness is equal to 8 inches. Okay. And the limits is 0, Y, and it goes up to 5.0153 inches. Okay, so that is the part we're going to do. Okay, so as I said, is the limits is controlled by the thickness. Okay, so when we write out the cube of Y, or Q, first moment of area about the z-axis as a function of Y, so the width is what? 6. The Y bar is 5 point, no, sorry, the depth is 5.1053 minus Y, okay, and the Y bar is 5.1053 plus by Y multiplied by half. Okay, so this is our width, this is our depth, this term over here is our Y bar. Okay, so when that's the case, you formulate this out, you calculate. So 5.1053 squared times 6 times 0.5 is equal to 78 point. I get 78 point. Is it 6336? No, the width is not 6, Eugene. The width is 8. Okay. So 8 times 1.1053 squared times 0.5 is equal to 104.25. Or 256. Then minus by 4y squared. Okay. So once you got this, the rest is straightforward already. So the shear as a function of y, this will be equal to v. So the v given is 35 times 10 to the power 3 multiplied by 104.256 minus 4y squared divided by 872.49, and then we have a thickness of 8. Okay, so 35 power 3 times 104.256 divided by 872.49. Wait, 35 power 3 times 104.256 divided by 872.49 divided by 8 is equal to 522.77 or 0.78 minus 20.058 y squared. Okay. So now we consider below the centroid, right? And now when t is equal to 8 inches, okay, so 0 to y, and then this height over here is 8 minus 5.1053. So 8 minus 5.1053 is equal to 2.8947. Okay. So now we just finished the top part. We are doing the bottom part just up to here, where the thickness is still 8 inch. Okay, so this is again the limit. Okay, so again QZ Y, the width, now this become 2.8947 minus Y 2.8947 plus by Y multiplied by half. Okay. So 8 times by 2.8947 squared times 0.5 is equal to 33.517. I do it again. 2.8947 times by 2.8947 times 8 divided by 2, 33.517 minus by 4y squared. Okay. So now your shear stress at y is equal to 35 times 10 to the power 3, 33.517 minus 4y squared, and the whole thing divided by 872.49 divided by 8. Okay, so this will be 35 power 3 times 33.517 divided by 872.49 divided by 8 is equal to 168.33 8 minus, let me do it again. Yep. Then it's 20.058 y squared. Okay. So you got that equation now. Okay. So now if I were to substitute Okay, I'm going to try this. Okay, I'm not done this problem yet. Okay. So if I'm going to, so I call this equation number 1. I call this equation number 2.